Thank you. Yeah. Hi, all. Thank you for chiming in. So my name is Gutbrod, and I'm a PhD student at OTH Regensburg in Germany, where my goal is to enhance the trustworthiness of AI models in medical imaging. But first of all, I want to thank Voxel 51 for making this series possible and giving me the chance to present our work, where we established medical imaging benchmarks for out-of-distribution detection. And also a big thank you to my co-authors, David Trauber and Danilo Weber-Nunes, and also to the best PhD advisor in the universe, Christoph Pan. So why should we care about OOD detection? Typically, AI models assume that the data during inference is similar to the known training data distribution. So here we can see the training data. And here we see test data, which is assumed to be quite similar to the training data. However, in reality, AI models often face some kind of distribution shift after deployment. And in these scenarios, the outputs of the models are no longer reliable and trustworthy. And the model performance quickly degrades. So, of course, one possible solution is to just make the models more robust so that the models generalize better to unseen factors. However, this might be infeasible. For instance, especially in the medical field, due to data scarcity, and we just don't know which underlying distribution shifts lie in wait in the future. So it is quite hard to make our models more robust against any possible shift. Another way to solve this is to detect if an AI prediction is unreliable. And for instance, in the case of an OOD input, then we can flag these inputs for manual review. And we think, especially in the medical field, we see this as a valid option because AI tools should not be used without oversight anyway. So the clinician is there and can just take over control. So to give an informal definition for out-of-distribution detection, we just want to identify inputs that differ from the training distribution. And the typical approach for this is that we define some kind of scoring function that gives back a scalar value with high scores for in-distribution and low scores for out-of-distribution data. And then we decide on a threshold value and separate ID from OOD using this threshold, which is what we can see below. And on the left, the OOD distribution, and on the right, some ID distribution with the threshold in the middle. And this threshold value is usually chosen so that 95% of the in-distribution data is correctly classified as in-distribution. As we can see, there has been a rise in popularity for this topic in the last few years. So those are the OOD detection publications in Google Scholar from 2020 onwards. However, to compare the performance of all those different methods that have been published, a fair and standardized benchmark is necessary. And that is what the authors of the existing benchmark OpenOOD did. This framework covers datasets with natural images like CFR10 or 100 or ImageNet, and compares these in-distribution datasets to various well-known OOD datasets, like on the right side. But what we can also see is this benchmark does not cover medical imaging at all, but only natural images. Initially, we wanted to improve upon an existing OOD detection method. However, given these available benchmarks on natural images, there was no way to really evaluate or know which of those methods actually performs well in our medical imaging domains. And this question and problem led us to the development of OpenMIBOOD, our medical imaging benchmarks for out-of-distribution detection. But so to even be able to detect if something is out of distribution, we first need an in-distribution dataset and also in-distribution classification model. And for our first medical imaging benchmark, we use the Midok dataset, which contains histopathological images. And for this classification model, we try to predict if a cell is a mitotic cell and a mitotic cell lookalike or a normal cell or background. And mitotic cells are cells that are in the process of dividing themselves. And mitotic cell lookalikes are just cells that look like mitotic cells, but are actually only imposter cells. And yeah, on the right, we see the in-distribution data with the gray circles. And as our first category for out-of-distributionness, we have the covariate shifted in-distribution data. And this means this data has exactly the same type of cells, but a covariate shift happened. And this can possibly happen or caused by image quality issues, or if the image is corrupted some way, or if the images are preprocessed differently, if the images stem from different subject groups, or as in our case, it can stem from a different acquisition device or scanner. And here the colorization, contrast, or sharpness of the depicted cells is different from our in-distribution data. But due to their similarity, we still expect the CSID data to be quite close to our original data distribution, and that we can see on the right with the green squares. Our second category covers semantically shifted data. This is also commonly called near-OOD data. And this kind of shift is usually caused if the input data depicts a novel class or concept. In our case, the types of cells differ. So for our in-distribution data, we only had breast cells. And in the near-OOD data, we have different kind of cells like lung or brain, skin cells. And these all have a different cell morphology. And besides these, we also have cells captured with different acquisition devices, and also coming from a different species, in this case, canine species. And well, we expect such data to be distinct from our training distribution, but still with some significant overlap, as can be seen by the blue triangles. And our final category covers context shift. And that is often described as far-OOD data. And in medical imaging, this shift can happen if a clinician uses an AI model on a completely different kind of data, let's say. And for this category, we selected two data sets with different cell extraction techniques of the cells compared to our in-distribution data. And here, due to the nature of far-OOD data, we don't expect any similarities between the far-OOD and ID data, which I tried to show with the uniformly distributed crosses for the far-OOD data in the picture. And so, but why did we design the benchmark in this way? And we think this section here is highly relevant in medical AI, because if we can catch these OOD cases, we can prevent misdiagnosis, we can build trust with clinicians and patients, and we can even support regulatory compliance. And the far-OOD setting is maybe not so important, because these cases can basically only happen if there was some kind of user mistake. However, it's still interesting if the OOD detection methods are capable of detecting these larger shifts as well. So to give an example of how OOD data can affect the performance of a medical AI in clinical practice, we evaluated our classification model for the mitotic cells benchmark, our first benchmark. And first on our in-distribution data, we reached human level performance of roughly 82%. But as soon as we evaluate the performance on the CSID data, where the only difference is a different scanner from another manufacturer, the F1 score decreases already by almost 8%. And if we then evaluate on the near-OOD setting, and in this case, even on the setting where the only change is the cell type, so the cell type is skin cancer instead of breast cancer, we see a decrease of almost 17% in F1. And the real problem here is that these errors are hidden from the clinician somewhat. It might be that the clinician just knows that the AI can detect mitotic cells with human expert level performance, but as soon as the underlying data distribution changes, the performance degrades, as we can see, and the clinician won't know this, won't know if the AI detected too many or too few of those mitotic cells. And this in turn will directly affect the treatment plan of the patient. So in our work, we introduced not only the histopathological benchmark from just now, but also one with endoscopical images and another with MRI 3D scans. So for the endoscopic benchmark, the second row here, we used the Fekir challenge dataset, and here the base task is to classify surgical instruments. And for CSID, we selected frames that have varying levels of smoke intensity. And for near-OOD, we have different instruments, so different from the in-distribution instruments, and as well as new organs, and again, a different species. And for the far-OOD category, we use a data set showing endoscopic images from inside the colon, as well as surgical procedures involving the eye. And the base task of our 3D MRI benchmark is to classify if a patient has Alzheimer's disease or if he is healthy. And for CSID, we have a different MRI modality as well as a distinct scanner. And for near-OOD, we have stroke anomalies and tumor anomalies and CT data instead of MRI data. And finally, for far-OOD, we used MRI scans of completely different areas of concern. Having all this, then we evaluated 24 different OOD detection methods. And those we categorized into feature-based methods, classification-based methods, and hybrid methods. So feature-based methods typically rely on embeddings of our data, for example, the penultimate feature layer from a ResNet, the output of this layer. And for instance, we can calculate the cluster mean of our data and calculate the distance to our testing data, and for instance, in this case, the near-OOD data. And this distance then is our S of X. And for the classification-based methods, there's the underlying assumption that ID data produces higher probabilities or logits than OOD data. And for the ID data, we can see an actual grasper instrument, and the probability for the grasper class is quite high. So this would be the idea. And whereas for an unknown instrument from an OOD dataset, we would like to see that the model distributes its probabilities or logits more evenly. So And then these probabilities or logits are then used in some way as our S of x. And for instance, by using just the maximum probability. And finally, the hybrid approaches combine both of these information sources in some way. And after analyzing the results on those 24 methods and 3 categories, we found that the feature-based methods on average outperform the other 2 categories in all 3 OOD evaluation settings. So this diagram shows the average AU ROC over our 3 medical imaging benchmarks, where we can see quite a distinct performance boost for the feature-based methods. However, because we think the near-OOD setting is the most relevant one, we focused our further analysis on this setting. And in this near-OOD setting, we even have a special case in our benchmarks I'd like to talk about briefly. For instance, in the second row, the FECI benchmark has not only a semantic shift here coming from the novel instruments, but there is also a covariate shift because the acquisition device, or the endoscopic, the camera, and also the hospital are different than in our ID dataset. And the same goes for the third benchmark, where the stroke anomalies or the tumor anomalies all come from different scanning devices compared to our in-distribution data. But for our first benchmark, we were able to split the near-OOD into a section that has only a semantic shift and no covariate shift at all. And that is because the data comes from the same institute and was acquired using the same hardware. So the only difference here is actually really the cell type. And in comparison, the remainder of this near-OOD section also has different scanners from different institutes. So having said this, we analyzed these 2 cases independently, and we can see that the feature-based methods rely a lot on distribution differences coming from covariate shift, where we can see if we only evaluate on the semantic shift, the performance is roughly equal to classification-based and hybrid. But as soon as the covariate distribution shift comes into play, the feature-based methods can capitalize on this. In comparison, the classification-based and hybrid methods are not able to capitalize on those shifts at all. And finally, we wanted to answer our initial question. How does the performance of these methods differ between natural images and medical images? And for this, we also evaluated all methods on the ImageNet 1K benchmark from OpenMIBOOD. And we found that feature-based methods excel in medical imaging and don't work so good with natural images, while the classification-based methods excel on natural images and perform way worse in medical imaging. So we give the answer to the question if the performance from natural imaging benchmarks transfers to the medical domain in this single scatter plot. It does not transfer. The scatter plot shows the ranking on each of the benchmarks. So the x-axis shows the average rank on our 3 medical imaging benchmarks, while the y-axis shows the ranking for the natural images benchmark. And ideally, we would like to have a method that is robust and lies in this lower left corner here. So ideally, rank 1 for both domains. But what we see are 2 clusters: the feature-based methods that occupy the first ranks on the medical benchmarks, and the classification and hybrid methods that perform way better on the natural images. So next, we try to understand where this difference in classification-based performance comes from. And for this, let's recall the assumption of the classification-based methods where the ID data should produce higher probabilities than the OOD data. And for instance, we can look at our results for images where there is no instrument for the second benchmark with the fake dataset. So as soon as there is no instrument in the frame, we get roughly the same probabilities on average. And I guess this is understandable because there is no instrument in the frame. So actually the model is doing its job and correctly assigning this class, even though the underlying data is completely out of distribution. But of course, this also makes it impossible to use classification-based statistics to differentiate between ID and OOD. So we think this is just a problem of the medical imaging domain, where we often need such a, let's call it fallback class. And then if the model only really focus on the instruments, in this case, it can just put everything else under the no instrument class, even OOD data, with a high probability, which in turn then makes it impossible to differentiate. But if we look at images where there is an unknown instrument present, so for example, the near-OOD images that we saw earlier, we can see that the probabilities for these unknown instruments are even higher for the ID images that show the Grasper instruments. So every time there is an unknown instrument, not every time, but a lot of times, there's an unknown instrument, the model assigns a high probability to the Grasper class. So, and we noticed this bias of our model toward assigning these unknown instruments to the Grasper class. And on the right, we can see a t-SNE visualization of the feature space of our classification model. And yeah, here the bias becomes clear. And of course, this again violates the assumption that OOD data should produce the lower probabilities than ID data. Okay, so with this, I'd like to mention that all our work is completely open source, and you can clone our repository and run your own experiment using our medical imaging benchmarks. And yeah, I'd like to scroll real quick over our repository on GitHub, where you can see we linked the paper and the original framework. You can see all our benchmarks, how we designed them. You can find the links to all the data sets, and again, also all the links to the publications of the methods, the results from our paper, and we released download scripts for the different data sets, all the sources of the data sets, and also installation instructions. And as well, of course, our pre-trained classification models so that everything can be reproduced. So yeah, thank you very much, and I'm open for any questions.